Thanks, Jordi, for the invitation. Thanks to HPC now for having me today. I've been following HPC now from the very beginning, so for me it's like a huge event, and I'm really thank you for being here. So, who am I? I'm one of the 600 workers of BSC, and I had the opportunity to work with 2 of the 4 departments we have in the center. I've been mostly involved with performance analysis, but since 2016, I've been working with the HPC software development group in the case department for computer applications for science and engineering, and we'll be doing a lot of porting and optimization of the code. So I'm bringing the knowledge from computer science to the engineering side. The work I'm presenting today is not my work, like my own. I'm part of a not so big team. We have HPC software engineering in one side and geosciences applications on the other hand. And we have been working together from the very beginning of Barcelona Supercomputing Center. This is a group that has almost the 15 years that the center has. Right now, we are 3 engineers, well, 4 if I count myself, Mauricio, and then 2 geophysicists, 1 computer science engineer with a background in geophysics, and another geoscience expert. And of course, we have a few people abroad in Intel and ARM and NVIDIA, so we always have help with the different architectures. Today, I want to present you both BSIT and GeNESiS. Those are our development frameworks, but I need to put you a bit on the history of how we have evolved from the very beginning to these 2 frameworks, how reliable they are, and how flexible we want them to be. So when we are talking about software development, we always targeting like the very right corner. We need the software to be efficient, to be reliable, to be scalable, and to be precise. So in the case of numerical simulations, all this stuff are important. Sometimes we just want that the results go well, but when you're running a code in an HPC machine, you not only need the result to be good, you want to take advantage of the whole machine. If not, if you're paying for these hours, you're wasting a lot of money. Where are we? How big are our codes? In terms of 100,000 lines, BSIT, the 2 codes in the case department are BSIT and ELIA. ELIA is for molecular dynamics. BSIT is for more wave propagation simulations. We are around 500,000 of lines of code. ELIA has a bigger development team behind them, so they have a lot of fingers in everything. And BSIT have been evolving from the very beginning. It has a peak of development, and now it's like really steady. Of course, physical problems are getting bigger. We always want to simulate complex scenarios, larger grids, more precise simulations of materials, or wind, or forecasts, and so on. Of course, that leads to complex software. So the software is every time bigger, more complex, and if you include the heterogeneous architectures that are available in the market, then you have like kind of an explosive combination. So everything is getting bigger in all dimensions, so you need to cope with it. Of course, that leads to hard to maintain, hard to extend. The learning curve is steep, so putting the developer hat is like an ecosystem really hard to chew. Why wave propagation simulations in the case of our specific target? They are widely used in the industry, and of course they are really computational intensive. Later on we have seen that they are also memory intensive. They are popular for wave propagations of electromagnetic and seismic. So it can be used for oil and gas industry, and it can be used for earthquakes in this case. Why are we interested in wave? Wave go through the ground, and when they bounce with some material, they collect all these distortions and come back to the surface and bring with the wave all the information about what's below the surface. So you need always geophysicists to interpret this data. And of course, you need the simulators to see if this data is precise. What we used to do, we used to go and drill a hole, put a microphone, and then shoot the ground and measure how this wave bounce. But this is costly, and if you want to do that offshore, that's kind of difficult to drill below the sea. And I don't know, in the Mexican coast, it's not an easy task. Therefore, we need always computer simulations, and it's cheaper. This map of the surface combines not only the simulation. You always need a set of experts. We had really good collaboration with the industry. So in the case of oil and gas, all our simulations have been checked from people from the industry. And when you move to a 2D scenario to a 3D scenario, it gets complex. And when you want a finer wavelength to get more information about what's going on below the surface, then your executions get more costly. In one slide, we have the summary of what has been done in wave propagation since 20 years ago. They started with reverse time migration, where they had some sort of simulation and a very good photograph of the subsurface, and they iterated on it and get a really good image of what's going on down the soil. Of course, as I said, this is expensive in terms of drilling costs and deploying all the engineers on the field, so it gets a lot of work behind. Then you have forward modeling. This is about 10 years ago, more or less, where you had a picture and you want to discern from this picture what are the materials the captured on that picture. And lately, we have full waveform inversion, where you get a not so good picture of the underground, a pretty good simulation model, and then when you combine these two, you get close to the reality image of what's below the ground. Why elastic? Because this has evolved, and in the beginning it was reverse time migration with only acoustic. We measured the wave only in 2 dimensions. It bounced and you measure, and that's it. But if you imagine the ground is not fully solid, you have materials that can bend, that can get distortion, that depending on the pressure of the ground, it changes. You can imagine elastic and the simulations in an elastic scenario, like when you're pressing an eraser gum. When you do this, the eraser goes in this direction, in that direction, and also in this direction. So you need to see how compressible the wave it is. That's why we use elastic simulations. And anisotropic, because you need to consider that there's not only one material below the ground. You have rock, you have sand, you have water, you have salt. So the density of all these materials is different. So and the way these waves behave when they hit this kind of material changes. So when we do this, of course, we obtain more detail. That's good for us as developers and for the industry. But of course, it gets more costly in terms of computational cost. Both computational and memory terms. The other pillar when we are targeting numerical simulations, every year we're having new flavors of architectures. Only in BSC, we are kind of lucky because we have Mare Nostrum 4 and we have the combination of well, Intel and IBM architectures and also NVIDIA. So we have a very nice general processor, the Xeon Platinum, the Skylex for the name. So most Mare Nostrum 4 is Xeon Platinum. These are not cheap processors, but they are fast, and the good thing is that they share the instruction set with the KNLs. We were expecting to have KNH here, but that project was shut down with Intel, so that's why we have only Xeon 5s in Mare Nostrum 4. Xeon 5s are cheaper, faster, as they are sharing the instruction set that general purpose processor, so you can move code easily from one to another. And we will see in some results that as they have a really good memory in chip, they provide really good results with not too much effort. And of course, the Power 9 with the secret weapon is the NVIDIA Volta V100. They are really, really good. As the preliminary result we have been collecting from this part of Mare Nostrum are really promising in terms of the accelerators. All this is around 13 petaflops, and hopefully Mare Nostrum 5, that was approved last week, will multiply this by 15 or 17, the power capacity. Okay, what's BSIT? Initially, BSIT was 2 kernels, 6 production chains, the whole workflow of simulating a different shots in a field. And well, at the beginning were like 5 people involved in it, and consider only the cell, because it was from the very beginning of Mare Nostrum. We have Mare Nostrum 2, Mare Nostrum 1, that were cell-based. And of course, it took 4 years of development to get to this state. It was a tough process and a slow process every time you need to migrate some part of the code to another architecture, or you want to include a new simulation model. So we decided to generate a framework that could tackle all the 3 forward modeling, RTM and full waveform inversion easily, and leave to the developers to implement their solutions in a more straightforward and more concise way. We conceive the framework as 2 pieces. The node part was focused only on solving the wave propagation problem that will be executed in one node. And then the workflow on one problem, and then the workflow level that will handle how data is distributed among the processors, how they are connected between them. This is a pretty much embarrassingly parallel terms of logging, scheduling, debugging, and some profiling. So starting from one need, we decide to create a box where we can put pieces depending on the problem we want to solve. And of course, in less than 4 years, we multiplied per 20 the available kernels, the different problems we were tackling, and of course, the different architectures that we were attacking at that moment. And the number of people was only doubled. So it's a framework. This kind of framework is providing to the developers a good tool to evolve his or her code easily and fastly, and of course having a robust implementations. How robust is this? We had the opportunity, well now 3 years ago, to use whole Mare Nostrum 3 for one simulation. This was an expensive simulation that the industry was interested on, And we had a lot of technical problems the week before to have it running. But the day they said, OK, the machine is yours, we started our simulation. And this is the usual workload of Mare Nostrum. I'm talking about Mare Nostrum 3. And this is with the workload of Mare Nostrum with our simulation running. So it's almost at 100% of resource utilization. We were using, of course, elastic modeling. In terms of memory usage, network usage, to the left is the regular use of the machine, and this is the network usage when the elastic modeling simulation was running, and we were getting 1.55 terabytes per second of movement in the network. So everybody was communicating with everybody, and everything was moving. Yeah, below or numerical simulation, they are stencil-based, so you're always communicating to your network. So communication is a really huge part of our code. I really like this slide. This is the actual load of the machine. How was it behaving when we had the simulation running? Pink is like up and running. Blue are starting to be used, and cells were not allocated. So we actually had almost the whole machine for ourselves. We were asking to have Mare Nostrum 4, but we haven't had time to get those slides. I will go quick with these slides because what I wanted to share is we have been tackling all the architectures available, and what we have been mainly doing is like applying all the from-the-book optimizations to our kernels and see how they behave in the architecture. So this is quite old. This is IKNC, but we start testing how it behaves when we are like enabling OpenMP, how many threads we are using, if we are using prefetching, and so on, and how we compare that evolution of performance with a general purpose architecture. This one was a more deep study we did with the KNLs because we had a collaboration with Intel, and they have a really nice optimization technique called vector folding, because as we are stencil-based, it collapses all the stencils and try to compute them the most efficient way. So we were obtaining this much of performance. In the terminology here is regarding the efficiency of the simulation, how many megacells I can calculate per second. This is not speed up, but it's like the throughput of the process of the simulation itself. Of course, vector folding gives the highest advantage, but it's really hard to implement, and it's completely tightly coupled to the architecture. So this is good for KNLs. If you want to try it for Skylakes, for example, you need to do a lot of study on it and try to implement it, taking into account how the different memory architecture will get advantage of it. And of course, when we observe the peak performance of one architecture, in this case, this is the roofline model of the KNLs, you expect always to be like here. These are performance bound by the memory. You can do all the optimizations you want that you won't break the ceiling, or these are processor bound optimizations. In our case, by applying all our optimizations, we noticed that we were always here. We are fully memory bound. So this is the maximum performance attainable for our numerical simulation in this sort of architecture. So the closest we were was over here. We thought that with the Skylake, we will be like, okay, we can do some modifications and run it on a Skylake and see how good it goes, and it should go better than the KNLs. It wasn't that way. This is the best speed up we get with the Skylakes. and still KNLs were way better, and this is because the high bandwidth memory that the KNLs have within. And the latest analysis we had was about Power 9. So if we run our kernels in a Power 9, we need to do a lot of optimizations to actually start to get good performance. But with the Voltas, and we had really good help from the people from NVIDIA working in BSC, we really multiplied by four the performance with minor optimization. So this is the next line that we will be following. So BSIT, it's robust, it's flexible. Well, it's robust and it scales well. When we have the numerical simulations implemented on it, you can go to almost every architecture that we had the opportunity to use. It runs well on petascale, and now with the exascale machine, we will be test again. We had the opportunity that the H kernel opens ways to optimize depending on which target architecture you want to use. But its learning curve is steep. It's not object-oriented. BSIT is implemented in C. It's an old code. And every time a user needs to implement a different numerical simulation using the framework, he or her needs to implement her own library. So this is costly in terms of time and deployment and development. So we proposed GeNESiS. GeNESiS is a more generic numerical engine simulation system. It's fully funded for a national project, so this has like 3 years project. It's finalizing this year. So we proposed the idea of GeNESiS, and we've been working on it since 2 years ago. And the idea is to have an ecosystem, like a larger ecosystem, that enables to the developers to implement any kind of numerical simulation, of course, targeting HPC platforms. The idea is to have really good and elegant code fast. The concept behind GeNESiS is like an onion, where you have more layers, and from the center to the outer layers, you're getting like from very, very detailed, very specific, to the more broad view of how it behaves in the HPC platform. So the core has basic building blocks of the numerical simulation. It targets resource allocation. It identifies which target hardware will you be running on it. Communicates a lot with domain decomposition, because when you're scaling, you need to share the meshes and to share the data between the different processors. And of course, it's targeting efficiency metrics and so on. Then you have all the numerical methods. From history, we've been working with partial differential equations. So we have finite elements and finite differences. So in this case, numerical methods will condense all the basic functions, matrices, coefficients, stencils, and so on, that will be like the mathematician part of the problem, like the physical part of the problem. Then you have the equations that basically decides if you're solving a wave propagation, incompressible flows, that kind of simulations. And we will provide some examples, and of course the user can decide to use our pieces to implement new solutions. And finally, what we call the problem, that's a whole picture overview that takes the consideration of executing. For in the case of wave propagation, core will be targeting one shot, problem will be concatenating more than one shot running in parallel. So this onion has been distributed among 4 frameworks. Those are EVA, Dan, Cain, and Abel. EVA is our environment for acceleration, because as we saw, Voltas is a really nice target to look at when executing numerical simulations. So basically, EVA covers the 4 layers of the onion. So only with EVA you can test the whole layers. It has support for all the HPC architecture we have right now. It provides all the information for the modeling, and domain decomposition. Then we have Cain. Cain is basically in charge of managing the meshes and how they are read and written for the problem. And Abel will tackle all the part of preprocessing and post-processing, because you do the simulation, you have some raw data that you need to process and then process again to be readable for the user. So that will be Abel. And finally, Adan, he will be handling all the whole workflow. So each one of these colors points to which part of the onion is being tackled for each one of the frameworks. GeNESiS is mostly written in C++, 11, and Python. So the idea is that all the functionalities implemented can be extended in any of the both languages. The idea is to provide a quick access to prototyping in Python, and test if your numerical simulation is working and if they will have like the results and the performance you're expecting, and then build a C++ version of it really quickly. So we have to take advantage of the part of efficiency and production pilers. The idea is to port from one to another, from the prototyping version to the production version really quick. If we see the history, it was usually a MATLAB script that went to C, and then you try to match all what's going on within a BSC library. So you had a lot of actors involved that was error-prone and really slow. So in the case, we want to use all the Python libraries available to be dynamic, to implement a first draft or first solution really quick, and then if it works well and you want to port it to C++, you can do it right now. The goal is to reduce the research and development cycle, and the secret weapon within it is Swig. So you can implement in Python, and once you have tested, with Swig you can generate a C++ version. So Eva and Cain has all the, it's almost everything implemented between Python and C++. Of course, by using C++ and or object-oriented processing, object-oriented programming, you can take advantage of all the design patterns, so you can be a more efficient software engineer. As I'm running out of time, we will cover only EVA, because it's the most solid framework right now. So what is a workflow in EVA? EVA will consider homogeneous architectures, solving one kernel, like one shot in RTM or one shot in FWY, or a whole campaign. So EVA will be able to provide everything in this regard. So it has a creation phase that detects what's the target architecture, what you're running. It has a configuration test that says, okay, the mesh you give me can be readable. It's what I'm expecting for my numerical problem. All the distribution among the workers that will be processing this, it's correct. How will be the communication protocol? All this information is handled by EVA and set up by EVA here. And then, of course, deploys the solver. So you have a lot of previous steps that the developer only need, the geophysicists or geoscientists. We only be focused here when it's deploying a numerical simulation. But the computer scientist or the engineer needs to provide all this configuration. We are providing a first skeleton to targeting all the architecture we have, and if you go to a new architecture, you will have to tune these pieces, but they will be provided by the very beginning. So how the workflow looks with Python or C++, then you have all the instantiation of EVA. I'm creating a solver, and it's kind of straightforward to read from one language to another. It's very clean, very elegant in that regard. Set the mesh. It's the only stage where Cain and Eva need to communicate, because Cain is handling all the input meshes. And of course, you start EVA, and EVA will handle everything and collect all the information that later on will be processed by AVE. The skeleton provided within EVA lets you to modify everything as you wish. If you're a user, you're like a geophysicist, you'll be only focused on the solver. You will change the numerical method, or you will change the type of element you're using, if it's triangular, if it's an hexahedral, and so on. But if you're a developer, you can actually touch how the links are connected, how the buffer and communication that between the nodes will behave, what's the cluster below, and of course the architecture. We provide the available architecture we have in-house, but if you have a new architecture and you want to set up, you only need to modify the configuration file, and it will up and run. We have tested EVA with 3 scenarios. Right now I brought the very simplest one. It's a 2D high order finite elements. It was done in-house, and actually this was one of these prototypes that were implemented 3 years ago in MATLAB, and it was very useful, but it wasn't taken to HPC platforms ever. So it's processing elastic wave, and the idea is to have a very old sequential proof of concept, usually implemented in MATLAB, to create a sequential prototype in Python. It will be more like agile to get into work with it, avoiding all the interaction within scientific libraries and so on. Usually going from here to here takes a couple of weeks, luckily. But going from here to a parallel evangelized code will take maybe 2 days, luckily. That's what we've seen with our experience. This is a master thesis that was presented a month ago, so that's what we're really working about. So that parallel evangelized code, how it behaves. In weak scaling, we are like increasing the problem as we increase the number of processes. It has a very good performance. We're about 256 MPI processes right now. So yeah, it has a very linear scalability, and thinking that we didn't think too much the optimization. We haven't started optimizing the code, the production code generated by EVA. We only took the sequential code, evangelized it, and run it. And just like out of the box, you get in weak scaling almost 80% of efficiency, so it's pretty good. And in strong scalability, we focus on the biggest problem we analyzed before and increased the number of MPIs again. And of course, it wasn't too costly to get up to 256 processes. This is about 80%, but then it starts to drop. So there's always a room for improvement. But as I said, this is out of the box. You get your new code, run it, and you were like around 80% of efficiency with 256 MPIs. What's the take-home message? Okay, GeNESiS is currently on development. It's a big project, and it's ambitious. We want to provide tools to get this process of implementing numerical codes as smooth as possible. And if you have a lot of experience with Python and numerical libraries with Python, and you have a sequential code that you're confident with it, you can actually really easily port it to an HPC machine in a couple of days. So that's the main message right now. Of course, we had the advantage. We had all the experience, the prior experience with BSIT, and with all the architecture flavors and with all the problems, and we have a really nice research group with geophysicists, so the part of numerical models is being led by them. So we have a mature code that now needs to get more agile. And we need, the idea of GeNESiS is to reduce that time span. I have a prototype, I have a couple of hours in Mare Nostrum 5, and so I needed to port it there quick. So GeNESiS will help you. And of course, this binomial between Python and C++ brings the best of the two worlds in one tool. You have a lot of numerical libraries and packages available, and then you have the solid and steady and efficient C++ code. So thank you.